Yeah, welcome to more Systronic Donnering. Still working on this thing. Last time I got it to work on the 1 volt, 10 volt, 100 volt ranges, more or less, subject to calibration, but the 1000 volts is all over the place, and I'm trying to track down what's causing that now. So I'll just turn it on, hope everything's in view. Now I'm just going to stick in a 5 to that first position, and then turn on the output, and we get 0.5 volts, very close. On the 1 volt range, on the 10 volt range we get 4.9, on the 100 volt range we get 50, and on the 1000 volt range we should get 500 volts. Dicky switches still, and we're getting overload, so way too much. Let's turn that off. I'll make that a 1 in this position. So now on the 1 volt range, 100 millivolts, 10 volts we get 1 volt, 100 volt range we get 10 volts, on the 1000 volt range we should get 100 volts. We're getting 355, 150, yeah, much more than 100. So I'm trying to investigate that. And I've recently got a better understanding of how the feedback system in this thing works, how it takes the voltage here and compares it to the voltage here and ensures that the right voltage comes out depending on the range. It was a bit confusing when I first saw it, and I thought it was weird and wonderful stuff that I probably couldn't understand, but it turns out it's actually fairly straightforward. Let's have a look at that.
Looking at the block diagram for the instrument, the original fault that I found a few years ago was these FETs. 3 of them were bad, and just recently I found that this buffer was bad. The FETs are these 4 things here, and the buffer is this 7404 inverter there. The problem now lies somewhere in all this, because that's the only place where the 1000 volt range comes into play. When these 2 relays are both switched on, then we're in the 1000 volt range. This relay controls the output polarity, and this is the standby relay that enables the output. Yeah, it's all a bit hard to follow, and there's this cal switching assembly thing which when I first looked at I didn't quite understand, and I thought it was all a bit of voodoo. Recently I had a closer look at it. I have in the past tried to trace out how all that works. I came up with this. There's the 2 relays that control the range, and here's the feedback network, cal switches and blah blah blah. There's the output amplifiers. That didn't help a lot, except to tell me that the only difference between the 100 volt range, which works, and the 1000 volt range, which doesn't work, is that in the 100 volt range this wire here is connected, and in the 1000 volt range it isn't. And digging more deeply recently I came up with this. This is path for when everything's running at in the 1000 volt range. So we have this control voltage that comes in from the front panel. Essentially we type in 6 digits on the front panel. All zeros gives us a 0 volts there, all 9s gives us 7 volts. Call it a million. When we can type in from 0 to a million, and we get between 0 and 7 volts there, which goes straight into this analog device's building block op amp gizmo that drives the high voltage amplifier board, and that goes through all the relays to the output terminals, and there's a strap on that which connects the output to the sense terminal, and that goes back into this network through the cal switches, through that pot, and into the other side of this op amp. And then the op amp adjusts the high voltage amplifier accordingly to try and equalize these 2 input voltages. And when I looked at this cal switching assembly, and the description of it didn't make much sense to me, at least the way I read it, I thought it was a bit of voodoo, but actually it's quite simple. It's just 8 slide switches and 8 resistors, and what it does is you have 2 paths there and here, and the switches just select whether or not each of those resistors is in one path or the other. Looking at my latest redraw, it boils down to this. We have just 2 resistors, 3K and 7K. So if you stick 10 volts in there, you'll get 7 volts out there. So if you stick the full scale voltage in there for each range, which independent of range rather, it's just 0 to 7 volts. 7 volts for full scale. So on the 10 volt range, that should 7 volts there should represent 10 volts on the output. If that's fed back there through this, we've got a 10k divider. We tap it off at 7k, we get 7 volts. So those two voltages are equal, and we're with 10 volts output. Beautiful. Now those two resistors form a 10k resistor. Together with that 90k resistor forms a 10 to 1 divider on the 100 volt range. So if we select the 100 volt range, then we'll have 1/10 that voltage there, which will be 10 volts, and we know that that produces 7 volts here. So in that case, the output will be 100 volts. It will adjust everything so that we get 100 volts out going into this point, and 7 volts comes out here. Similarly, for the 1000 volt range, all this here adds up to 100k, and we've got 900k there, so it's again a 10 to 1 divider. If we select the 1000 volt range, 7 volts in here will make the amplifier adjust to, we've got 1000 volts going out there, which will divide down to 100 to 10 to 7 volts, same as the control voltage coming in, and that's how it should work, except only the 100 volt and 10 volt work. So that's the simplified form. Let's have a look at it in a little bit more detail. This here is what we're just looking at, this part. This is the 1 volt divider, which actually works by running the machine in the 10 volt range, but then dividing it through these two resistors with adjustment here to get 1/10 of that to provide the 1 volt range. That works more or less, so let's forget that. We're just talking about this part. Now, we've got some precision resistors here, which are all in a potted, made by Nude Virgins at Systronic. A couple of trim pots. There's the cal switch assembly and another trim pot. And that just goes into the amplifier, which comes back through the appropriate range switch, feeding back into this network. Here it is in physical form. There's the analog devices amplifier, the first part of that amplifier business, stage 1, and then that controls the high voltage amplifier board up there. There's the Nude Virgins created module with the 6 precision resistors, probably wire wound. There's the 3 trim pots that adjust for it, and there's the output relays. These two select the range. That one's the polarity, and that one's the output enable or standby relay. There's the 8 slide switches that form the cal switch assembly. Quick look at the amplifier. The high voltage amplifier looks like that. Bunch of high voltage resistors, and the schematic for that is there. I don't fully understand how this works. This part over here is current limiting. That's fairly straightforward, and there's a bunch of cascaded transistors to handle the 1500 volts. But this business here is not entirely clear to me, but it somehow switches for lower voltage that runs off the 140 volts supply to the output, and then as required it transitions to start drawing from the 1500 volt supply for output voltages greater than 140. So what I want to do now is monitor the input to this amplifier and the output terminal and try and work out whether there's a fault with how it divides through there, if it's producing the wrong input to the amplifier for a given output voltage, and then try and work out whether or not the fault's in the feedback network or in the amplifier. Maybe there's something wrong with this business here where it switches to the high voltage range of the 1500 volts, because that's the only other thing that's different in the 1000 volt range. Let's have a look.
Now, in order to see what's going on, I've soldered a couple of test pins onto the inputs to that analog devices amplifier, the U6 block thing, and analog ground. And I found that these little meters with their 10 mega ohm input impedance it's all right on the input coming from the feedback network. That's low impedance, so this doesn't affect it. But the control voltage coming out of the filter is very high impedance, and this 10 mega ohm impedance of this thing loads it down. So I'm going to use these bench meters, which on the 10 volt range are over a gig ohm input, so they won't load down that circuit too much. So what we've got here now, I'm going to type in a value there. I'll probably make it only 2 on the second digit, which will be 20 volts output on the 1000 volt range and then follow that back. Why deal with high voltages if we don't need to, especially since it produces much higher voltages than we ask for. So these 3 meters, this one is connected to the control input coming out of the filter, so that will represent directly the number we type in on the front panel here. This one's on the other input to the op amp, so that's the voltage coming back from the feedback network, the voltage divider, and the top meter will be the output voltage that it's sticking out on the terminals. So we should see that the voltage there is 7/1000ths of the voltage here, and that these two voltages should be equal. But that can't be right, because otherwise we put out the right voltage. So let's see what we can find out. So I'm going to put in just 0.02, switch that to the 1000 volt range. Well, let's look at the 100 volt range first. 0.02 on 100 volts, so we should be getting 2 volts out, and we do. We're getting 2 volts out, and the two inputs to the op amp are equal, as they should be, because the op amp is adjusting the high voltage amplifier output so that when it's divided comes down to here. Now this voltage here should be 7/100ths of that voltage. Work that out later. Now if I switch to the 1000 volt range, we should be getting 20 volts out, but we're getting 170. Yet these two voltages are still correct, still the same, and as they should be for the same number on the front panel. These should always be the same, and they are, but we're getting the wrong value out there. So it would seem that there's something wrong in the divider, because on the 1000 volt range that should be 1/7000th of what this is. And let's try and work out what those ratios actually are. Maybe I'll just put in a couple other values. Let's put in 1 in that first position, so that should be 10 volts on the output. If we put in 5, so it should be 50 volts output, we're getting 270. So yeah, something screwed. These numbers are right, so there's something wrong between dividing that down to this. The next thing to do is probe the voltages down there. They're the pins of the main resistor network, the potted block, and see that the voltages there correspond to what they should be at each tapping on the way down. And so I was trying to measure the voltages across the tappings on that potted resistance module with the 6 precision resistors in it, and even these guys with their high input impedance, that's only on the 1 ohm and the 1 volt and 10 volt range. Above that they're 10 meg ohms like everything else, and even that on the top outputs affected the output voltage. So as you go to different points there, you get different output voltages, and so it's hard to judge if things are right. But so I've been measuring the resistances across there, and some of it's a bit screwy. I'm now looking at these 3 trim pots which are sitting across some of the points on that. So I'm talking about these 3 trim pots in particular. They're the ones that connect to various points on this potted module, and they have wires from the end that go down the printed circuit board. So, and I'm getting some strange readings looking across the 3 wires on the PCB. This one had, if you remember, had 1 loose wire. That's the 1 volt adjust. I think this is the 100 volt adjust and the 1 kilovolt adjust, and that's the scale factor adjust. So yeah, those 4 pots, I'm getting some strange readings. So I'll just have another look at them to be sure. Yeah, digging around a little bit more, it seems to be just this 100 volt adjust trim pot that is causing an issue, which is screwy. And if I just look at across the total of the resistance, not across the wiper, we're getting 900k, and 900k across a 100 ohm resistor is not possible, so something wrong there. From the wiper to one end we're getting 61 ohms, and to the other end from the wiper 900k. So it's as if that trim pot has gone open circuit, and the side that's gone open circuit on is the part that goes up to the 1 kilovolt dividing resistances. The 100 volt range feedback goes into the centre tap on this, into the wiper, and the rest of the divider network is on the 61 ohm side of that. So, that side works, but above that it seems to be open. That's why I guess this kilovolt range isn't working. So if that's a 100 ohm resistor and it's currently adjusted to make 61 ohms from the wiper to one end, then from the wiper to the other end should be 39 ohms, not 900k. But if I just bodge on a 39k across those two terminals, that should make it work, shouldn't it? Let's try it.
And just for some quick context, I'm talking about this trim pot here. And as you can see, the 100 volt goes into its wiper, and it seems to be 61 ohms on this side and 900k on that side. So I'm guessing it's gone open in there. So what I'm going to do is just strap 39 ohms across from the wiper to that side, and that would make it very close to what it would have been if it was working, I think. And then, presumably, the 1000 volt range will start working properly. So let's try it.
So there's my little 39 ohm resistor from the wiper to the high side, the side that appears to have gone open circuit on that trim pot. And now comes the moment of truth. Ready to try it. Power on. And let's just put a 1 in that first position. Turn on the output. And we're getting 0.1 of a volt, 100 millivolts, correct. Go to the 10 volt range. 1 volt, correct. 100 volt range. 10 volts, correct. Now here's the test. 1000 volt range. Puts it in standby. Now we take it out of standby, we should get 100 volts. Bloody close. That could be it. Let's go to that first digit. Put in a 2. 200 volts. 3. 300 volts. You little ripper. 400. 500 rather. 600 volts. 7. Beauty. 999. So I've ordered new switches. Some of these are dicky as well. I'll replace all these, I think. Come on. Right. Put in 9999999 and put this to 999.6 volts. Well, it's only 300 millivolts off. That's not bad. Only 300 millivolts off with just a resistor bodged in. So, yeah, beauty.
So I've put all the covers back on. I'm letting the meters and the M107 warm up so we can compare the outputs. And I've left the bodge resistor in there for the moment because I've got to get some of these trim pots, or one of these trim pots, and they're fairly fancy pants looking ones with these leads coming out the top and this mounting system. Looking around, here's the L3059L style with the leads coming out. These things, all versions seem to cost about $12, but for these things you got to buy either 50 or 100 of them. I don't really want one of them. And so there's this Y version with the leads on the side, more traditional like there. So I'm hoping physically that and that these two are the same. They say common dimensions, so it looks like I could get that, and it's the same size as this. And then I see this panel mount option, which is what these things have with that frame around them, this metal frame riveted. I should be able to drill that out, and if everything lines up, I should be able to just put some bolts in and end up with a reasonable facsimile. Just the wires sticking out the side. I have to solder some flying leads onto that, and it should be a pretty good replacement. I thought these were some sort of a lock screw to hold it once it's been adjusted, but they're probably just a mounting system. I'll order one of these without the panel mounting, hardware. I should be able to bodge that off the old one. I'll put that in one day. I'm also getting new switches, so sooner or later I'll get this thing back together, and then it's going to need a recal, I'm pretty sure. So let's have a look at those meters now that they've warmed up. They've been warming up for maybe 3/4 of an hour, and yeah, pretty good agreements. These guys are always in pretty good close agreement, and they're disagreeing with this, so I guess using democracy, these guys win, and this one needs calibration. If you look at some of the, that's on the 10 volt range. If we go to 1 volt, so 0.12345 yeah, they're all in close agreement. 10 volts, 100 volts, 1000 volts. Nine, 8, 7, 6, 5, 4. Bit of disagreement there, but that's to be expected because we've got that bodge resistor in there. So yeah, new switches for here, new trim pot to replace the bodge resistor, and then do a recalibration by consensus. I'll go through the cal procedure, and wherever I need to measure what's coming out of that, I'll take whatever seems to be the consensus with these three and adjust accordingly. So I'm pretty pleased now that finally this thing seems to be in pretty good working order. That's why I don't mind spending a few more bob getting switches and the trim pot. So I hope you found this little saga interesting. If you did, please give it a like. Catch you later.